Thank you very much. Thank you for the kind introduction. Thank you for the organizer for having me here. Actually, it's always a pleasure. It's to come back to Pisa. Actually, I spent quite a nice period of my life here. Actually, and it's a city that a place that I love, in spite of what Dante used to say. Actually, he used to say there's okay. So we'll Okay, yeah, I'm talking. I tried to talk about this problem. So the fact that actually for initial data with positive cosmological constant that actually it should be the one that has been measured. So I mean the cosmological constant of the universe should be very small but positive actually. And yeah, for initial data like this, actually we essentially we don't know many things. And okay, also before starting, actually, I have to see that actually this research has been um, made with the contribution of the PRIN project, actually. So I have to show this slide, otherwise they ask me back the money. So in order to be safe, actually. No, but it's also a pleasure because I mean there are also other people here which are involved in the project. Carlos Inestrari, also Ettore Minguzzi, and also he's not here, but actually is part a big part of the project. Nicola Gigli in Sissa. It gives me the excuse to advertise a couple of things that we are going a couple of action that we are going to put in place this summer. So there will be a summer school in Trieste from July 13 to July 18, and then there will be also 3 days in Trento at the beginning of September. So for people who are interested, so you are more than welcome if you want to join these two summer schools, let's say. So and okay, let's start so with a quick recap on the setting on GR setting. So so that's these are the Einstein equation, okay, on a 4D Lorentzian manifold, okay, and so here you recognize the Einstein tensor. TAB is the so-called stress energy tensor, and I put also lambda, a term with the cosmological constant. So capital lambda will be the cosmological constant here. Okay, there is a lot of story about the fact that this term was introduced and then it was canceled and then reintroduced eventually. So, but actually, it is here. It matters to us actually, and these are the Einstein field equation. And of course, if you look to the initial data as a space like a hypersurface, at Riemannian space like hypersurface inside this Lorentzian 3D manifold, you have constraint given by the Gauss-Godazzi equation, and these constraints on the initial data are called the Einstein constraint equation. Okay, there are well-known results by Yvon Choquet-Bois, York, saying that if you have a tripole like this, so a Riemannian three-manifold with a 2-0 symmetric tensor, satisfying this relationship, okay, here capital K is the mean curvature, that's the norm of the second fundamental form, okay, if you have this equation satisfied on the initial data, then you can construct solution to the hyperbolic system of the Einstein field equation. Okay, and these terms as the interpretation, this correspond to T nu nu. Okay, this rho as the interpretation of an energy density, and and J, the component of J, okay, are the momentum density. Okay. And okay, here we are. I mean, in this talk, we will focus on a very special situation, which is the one of time symmetric initial data. So for us, K will be identical to 0. So we are looking to totally geodesic. I mean, our initial data will be totally geodesic in the evolution. Okay, and in this case, I mean, this constraint equation reduces to the following to the following requirement actually, and here is a prescribed scalar curvature equation in which you have the cosmological constant and the mass density, and there is a the dominant energy condition that we assume actually is telling that energy density should be greater than the length of the momentum density, right? And so for us, okay, after this introduction, from now on we'll focus on this a particular class of manifolds, so 3D Riemannian manifold whose scalar curvature has a lower bound given by twice the cosmological constant, right? Okay, so let me quick recap what is known in the most studied case, okay, which is the one with zero cosmological constant. So in this case, actually, much is known. So there is a very well established notion of mass that was introduced also in previous talks, the ADM mass, right? And for this mass, we have a beautiful statement like positive mass theorem, which are also endowed with our rigidity statement, right? So it's what to recall that you have this very famous, very well celebrated theorem. So you have a complete Riemannian manifold with no negative scalar curvature. If it is asymptotically flat in a precise sense, so the coefficient, you have a chart and infinity, and the coefficient decay toward the flat metric in an appropriate with an appropriate decay rate, okay, that's the optimal one. Okay, you can define the mass, and the mass turns out to be non-negative by this theorem. Moreover, okay, let me just, okay, here there's a famous expression actually. You can give a very convincing heuristic why this apparently weird things, actually weird object, actually has to do with the mass. So, but here, I mean, I would just want to focus on the fact that actually it's an expression involving first derivatives, okay? And actually what matters is that actually the fact that these terms is decaying compensate with the fact that the area of this coordinate sphere is growing. At the end, it gives a number, okay? So the rigidity statement is very important. So if the ADM mass is zero, then you have a complete characterization of the initial data as a 3D Euclidean space, as it is well known. Right, and so as was mentioned by Anna's talk yesterday, actually you have analogous result for asymptotic hyperbolic initial data. A lot of very interesting new things are coming out here. I beg your pardon. That was just I mean the old result actually, but I mean it's a very active field of research. Also, the one involving asymptotically hyperbolic initial data. Okay, in this case, the lower bound for the scalar curvature is -6. Okay, if we normalize the cosmological constant to be -3. Okay, so you have this notion of mass or mass aspects. Actually, for this you can prove positive mass theorem, and here, okay, we are interested also in a result, okay, due to minimum, okay, that I want to recall, okay, even before this result was given, even before the definition of the mass were given, okay, it is about the rigidity statement, okay, in the asymptotically hyperbolic positive mass theorem, right? So what's the setting? So it's the same. So you have a complete Riemannian manifold, scalar curvature larger than -6, and then you assume something that I mean I just phrased as strongly asymptotic hyperbolic. So meaning that your metric decay towards the one of the model solution, which will be, as you guess, the hyperbolic treat space. Okay, strongly enough. Okay, strongly enough means that I mean the first derivative and the second derivative they decay very fast, so that a possible mass-like expression. I mean, the mass was not defined yet. However, if the intuition says that the definition has to do with the decay of the first derivative, okay, if you assume that this first derivative of the metric decays sufficiently fast, so I don't want to enter into the detail of this definition, but if you are strongly decaying toward the model, then the mass should be zero, right? Whatever it is, whatever it will be, actually, and you characterize your manifold as the model space, right? So it's in the framework of a comparison theorem, okay, comparison geometry, okay, with rigidity statement, right? And right, and here here comes the problem. So here comes the problem, because then Minou proposed also a conjecture, a very famous conjecture, also for the case of positive cosmological constant. Okay, so you can conjecture a rigidity statement also without giving a notion of mass, right? So it makes sense. And so what's the conjecture in this case? Here the setting is a okay, maybe it's worth to recall that actually the model space in this case would be not the sphere but the hyperal sphere, okay, the sphere from the equator. So the model case here would be the sphere with the equator, and the equator can be interpreted in a relativistic framework as the so-called cosmological horizon. Okay, maybe okay. If time permits, we'll give you some intuition on this object. But for us, I mean, geometrically, it's very simple. It's just the equator, right? So it's minimal, unstable hypersurface S2 inside the tree manifold. So what the conjecture? So because here, okay, we don't have positive mass theory, we don't have notion of mass. However, okay, in this constant, so we have a compact tree manifold with non-empty boundary, smooth, minimal, and even more, if you like, and with scalar curvature greater than 6. Okay, if you normalize lambda to be 3, 2 lambda is 6, and actually Minou proposed okay, a statement like this. So mass 0 implies rigidity. So in this case, rigidity means being isometric to the upper sphere. Okay, and so the so how can we translate mass equal to 0 in this context? So according to some geometric intuition, let's say. So in the asymptotically hyperbolic case, you were just you were just imposing strong asymptotic decay, right? In this case, you impose that on the cosmological boundary, so on the equator, the sphere, the metric inducer on yeah on uh, what did I wrote? Yeah, yeah, okay. Here, the boundary. Yeah, so that would be the boundary. So the metric induced on the boundary is the one, is the round spherical metric on S2, and also the second fundamental form, the fundamental form of the boundary is 0. Second fundamental form has to do with the first derivative, first normal derivative of the metric, right? So that makes sense, right? So when you are that I mean, it could be a reasonable translation of being asymptotically flat with a strong decay. So the conjecture was that under this assumption, I mean, and this is supposed to translate this zero mass condition, then the metric is the round metric. It turns out to be false, right? So it's well known that actually Brandon, Makers, and Neves were able to construct a counterexample to this statement, right? And so I mean, the situation was very bad because we don't have a notion of mass, we don't have, of course, we don't have a positive mass here, but we don't also we also lost the intuition of the rigidity statement. The rigidity statement could be right, even though that would be, yeah. Then okay, it's worth mentioning that after this, I mean, there were a lot of results. Here I mentioned just one of the first one. So if you replace, if you I ask for stronger condition, for example, a stronger lower bound, instead of scalar curvature greater than 6, you ask Ricci curvature greater than 2 times g. Okay, then Hang and Wang were able to prove that actually the implication holds true. And also, I mean, there are several interesting contributions by other authors. There are very so as soon as you add something to this setting, so to this assumption, then you conclude. Okay. However, uh, here I want to describe a little bit this counterexample because there will be important also in the following discussion. So the counterexample are very clever, I would say, and also so maybe there will be, I mean, something very so a very natural possibility would be maybe, okay, here I'm asking maybe the decay that I'm asking, the decay, I mean the convergence toward the model, that I'm asking here is not strong enough. Maybe if I add a bunch of derivative here, okay, okay, maybe I can do it, right? And that's not the case, right? Because in the counterexample, okay, they construct a metric, a smooth metric in the half sphere. Yeah, unfortunately, the drawing is the lower half sphere, but actually, okay, you can do as you. So, but so here, so with the scalar curvature is strictly positive at some point, so it cannot be isomorphic to S3, and actually it coincides, okay, with the model metric, okay, on a band, okay. You have a band around, so a tubular neighbor of the cosmological horizon of the equator, if you like, okay, where the metric is precisely S3. So okay, so it doesn't matter how many derivative of the metric will vanish at the boundary. Okay, you can never do that, right? Even if you are, so maybe, so for example, a baby version of positive mass theorem is or the rigidity statement in the positive mass theorem is telling you that if you are definite, so if outside the compact set you are flat, okay, then you are R3 everywhere, right? So here would be the same. So if you're outside the, okay, if you are sufficiently close to the horizon and you assume you are round, then you are not round. So it doesn't work. Okay. Okay, and then there is a counter theorem to the counter example. Sorry. Now, after, I mean, the same year, actually, they provide, okay, they compensate. I mean, there is this positive result, okay, uh, which they can prove rigidity, actually. These are due to Brendel and Marquez, okay, if you stay sufficiently close to the North Pole, okay, there is a threshold, okay, in any dimension, right? So in a dimension, there is a threshold, if you consider a spherical capsule, something like this, so the portion of the surface of the S3 of DSN plus that lies above this this threshold, okay, for a domain like this, you can if you assume also there is also this further assumption. So if you are C too close to the round metric, then you conclude then up to a diffeomorphism, okay, you can you can put back your metric and the metric, so the metric is the round one up to a diffeomorphism, right? So it's not known whether the threshold is optimal. However, in dimension 3 is not, I mean, it's pretty large, right? So because the North Pole is, with this normalization is 1, here you are allowed to take only very small spherical cap. Okay, so I mean, but this gives me the excuse to introduce also the fact that um, not only the global rigidity is important, but also the local rigidity, right? So as was mentioned in Garrett's talk, also finding characterization of having zero quasi-local mass, whatever the quasi-local mass is, right? So it's important to look also for local version of the rigidity statement, and here there is a okay the maybe the most studied notion of quasi-local mass is the Hawking mass, okay, that you can actually define also in initial data with different cosmological constants. So the usual one would be the one that was mentioned also in Garrett's talk. It was the one with lambda equal to 0, but also you have this version, okay, that are also studied, okay, and essentially, okay, you have a domain. Sigma is the boundary of the domain. This quantity is supposed to somehow describe the mass content of the domain enclosed by sigma, right? So you have this okay, this usual term, right? And okay, so that's something very well known. So in 3D space, actually, you do have this rigidity statement because you know that you have the Wilmore inequality. So in R3, so if you have a closed hypersurface with zero Hawking mass, then it must be around sphere. Okay. And there, okay, and here also there is, I mean, another very famous result, which is due to Christodoulou Yao, saying that if you are in a three-manifold with a negative scalar curvature, okay, you consider a stable CMC sphere, then the Hawking mass of that sphere is non-negative, okay, and this, I mean, this is the usual one, so the one with lambda equal to 0. So maybe I write it because also for future purposes would be a certain moment important to recall this Hawking mass with cosmological constant. So that would be the square root of sigma over 16 pi times 1 minus 1 over 16 pi integral h square. And then you have the extra term, which is minus 2 lambda over 24 pi. Yeah, right. Times the area. Right. Okay. So, I mean, Bardring was suggesting, yeah, the problem of investigating the rigidity of this notion of quasi-local mass. And so essentially you are looking for a statement like this. So if you assume that the Hawking mass is 0 plus assumption, then uh, then sigma must be a round sphere, and the domain enclosed by sigma should be a geodesic ball in a space form, right? So depending on the sign of lambda. So if lambda is 0, is a ball in free space, or a ball in the sphere, or a ball in the hyperbolic space. And actually, it turns out that actually statement like this can be proven. Okay, there are this theorem by Sun, 2018. Okay, so here the Euclidean version. So you have a 3D manifold with a negative scalar curvature. Okay, and you have a stable CMC sphere. If you assume, I mean, this nearly round assumption, so yeah, it means that actually, yeah, the Gaussian curvature is the expected one. Okay, then you have implication like this that all true. So if the Hawking mass is 0, then you are isometric to a Euclidean ball inside. And maybe you can struggle whether you can replace this nearly round hypothesis with something else, something weaker. Okay, you have a hyperbolic version of the same statement with hyperbolic Hawking mass. Okay, and unfortunately, okay, here, sorry, also means the yeah there is a partial positive result also in the positive cosmological case, okay, in which due to Melo in 2023, so very recent result, so the same setting with positive lower bound for the scalar curvature, you have a stable CMC sphere nearly round in that sense. Hawking mass is 0, then what you can conclude, it was written, I don't know where, it disappeared, that you can conclude that the boundary, so sigma is isometric to a sphere, okay? But you cannot conclude something inside, right? So that's, I mean, that's because of the counterexample, right? Because of the counter. So imagine you take the equator in the Brendel-Marcus-Neves example. So I know it's not stable, or that is not stable. In any case, it is false that in general you have the strong conclusion. So the fact that the inside is the spherical ball. So okay, okay. Right. So also, I mean, so also locally the problem. So you have global problem, showed by counter example, but also the local problem is so the local rigidity with the extra assumption of being nearly round is not. You cannot make it. Okay. So it's, I mean, a lot of question and open problems. So let me, okay, recall, yeah, something that was already discussed in the previous talk. So the fact that the Hawking mass enjoy a very nice monotonicity property along the inverse mean curvature flow. So you flow the hypersurface, okay, with this speed. So the speed is given by 1 over h in the normal direction. So the area increases exponentially. That's well known. And and the Hawking mass, I mean, what I want to say here is that actually this quantity here, so continues to be monotonically in non-decreasing. So also in the case with where the cosmological constant is not necessarily 1. So in other terms, the Gauge computation actually carries on also in this context. And here, okay, here's the derivative. Okay, these are the usual term. This one you treat with the Gauss-Bonnet. These are positive. And here, okay, you see, okay, you have this term here that is non-negative by the dominant energy condition. Okay, and actually, this is if you recall the first slide, this is that's the density matter, right? So the matter density, right? And actually, in the very famous work by Wisken and Mannen, actually, the weak theory of inverse curvature flow was established, and actually. Made this computation, the general computation also available for a proper flow, right? Because, I mean, here you can conclude something only if the flow exists smoothly for all time, which is, I mean, which is, I would say never the case. It's not true. I mean, it is the case only under a strong assumption on the initial data. And but here, I mean, fortunately, you have this theory in which, okay, we can consider weak solution to that equation and actually flow the hypersurface also in a very general, in a much broader context. Okay, with this theory, actually, you can prove also a positive mass theorem, right? So not only the Parent inequality, but also, I mean, if you consider an inverse curvature flow coming out of a point, okay, with a pole somehow, okay, you follow uh, the small geodesic sphere. Okay, you use the monotonicity property that actually survives also in the case of weak when you when you possibly may experience jumps as it happens in the weak inverse curvature flow. Actually, you can prove this positive mass theorem, right? So because at the beginning the Hawking mass is zero, at the point it is zero, it is easy to verify, and then this by monotonicity, okay, you have this inequality, and in the end, it is well known that the Hawking mass gives a lower bound for the ADM mass, right? So it's an independent proof of the positive mass theorem. And if you consider, of course, weak inverse curvature flow coming out of an horizon, you get a stronger statement, which is the Penrose inequality, the Riemannian Penrose inequality. Okay, so the question is, maybe we can adapt this argument, this beautiful argument, also to the case where lambda is positive. So can we run the same strategy somehow, okay, in the context that we're interested in? So a tree manifold with positive lower bound for the scalar curvature and an empty boundary. Unfortunately, I think that the impression is that the counterexample actually may cause big troubles if you want to reply this strategy. Why? Because okay, imagine that you can run the flow from here up to the boundary. Here, capital T could be also plus infinity. Okay, so you want a flow, okay, starting from a point by inverse mean curvature. Why? Because you know that the Hawking mass is not increasing. Also in that case, and you want to somehow grab all the mass content of the space, okay, landing on the boundary of on the cosmological boundary. So imagine that for large t or even for t going to plus infinity, okay, you land on the. As for the inverse mean curvature flow, in this case, where you know that actually for large time you approach large sphere, okay, in the asymptotically flat end, right? So in the end you grab all the mass content of your initial data. So imagine you can do something like this also in that context. However, due to initial data like this, in which you have region in which the scalar curvature is strictly above the lower bound, it happens that the mass, so the mass starts being zero at the pole, okay, then increases, maybe nothing happening here. However, when you cross this yellow region where the scalar curvature is positive, you have a term like this in the derivative, okay? So the derivative becomes strictly positive when you cross this part here, it could stay 0 up to here, but when you cross, it is sure that when you cross this yellow region, the derivative becomes strictly positive, and also the mass becomes strictly positive, right? In the Giraud computation, that was the one that, yeah, this one. So, okay, here's the derivative, here's this term here, okay, and okay, the derivative, when you cross the yellow region, becomes strictly positive, so also the value of the mass, that at the beginning was 0, it becomes positive after crossing that region. And that's the problem, because at the end, okay, if you land on the boundary, the Hawking mass of the boundary of the cosmological boundary can be computed explicitly, actually. It turns out to be 0, okay? So that's a contradiction, right? So so it's not really a contradiction, but actually it's something that uh, actually contradicts the possibility of running a similar strategy in that situation, right? Okay, and here I want to mention a result that maybe come to rescue. Okay, so we together with Virginia Agostiniani okay, I forgot to say that what I'm talking about is a joint work with Virginia. Okay, we are about to complete the editing of the paper. Is a joint work with Virginia and Stefano Borghini, Virginia Agostiniani and Stefano Borghini. Sorry. And okay, but together with Virginia and Francesco Ronzio, we proposed this green function proof of the positive mass theorem, okay, in which essentially you consider the level set flow of a green function. So you have a 3D asymptotically flat manifold with no negative scalar curvature. You can consider the green function with some pole, okay, and then you consider the level set flow. So here's the graph of u, and corresponding to the graph of u, you have the level set. These are the level set of the green function inside your manifold, okay, and you flow this as so you consider this hypersurface as flowing by the level set flow of this function, so they kind of mimic the behavior of the inverse curvature flow. Okay, it's very convenient to consider this change of variables, because for a reason that will be clear in a while. So if so, here's your green function. You know that it exists. It's very simple. So you consider this change of variables. You set w equal minus log u, and right. That's the function. The level sets function of w are the level set function of u, and you can introduce that was maybe the main novelty of the paper, a monotonicity formula holding along this level set flow, okay, as the Hawking mass is monotone along the inverse curvature flow, right? And it is basically, so you have very similar terms if you remember the formula, and you have some extra term here, okay, which turns out to be non-negative. And also you can observe that in the model situation in R3, this is just 0, right? Just because it is like, so you compute explicitly everything, so right? And also you have p version of this monotonicity formula. So you consider p harmonic function, okay? You change the variable in the same fashion, okay? You get a w which behaves like this, okay? And this change of variable was considered by Roger Moser in 2007, because you can use essentially this p harmonic function up to change of variable to approximate solution to the inverse curvature flow, and eventually prove existence of the inverse curvature flow. Because when you let p goes to 1 formally, this becomes the divergence of the normal. We show in the next slide, and this becomes, so the divergence of the normal of a level set is the mean curvature, and this becomes the gradient of the function. So h equal to the gradient of the function means that the level set flow is actually the inverse curvature flow. And right, also for the p harmonic case, you can do that actually. And okay, you have to work a little bit harder, but actually you get rewarded in the sense that actually with the p harmonic, with harmonic function, you can prove positive mass theorem. With the p harmonic function, you can reproduce a version of the Riemannian pairs inequality, and this is a contribution with Virginia, Francesca, and Carlo Mantegazza. Okay, here's the formal limit that I was mentioning, right? So here's the P Laplacian. So that's what the idea in Moser paper. Okay, so it's a P up to a, remember that this WP up to a change of variable is a P harmonic function. So the existence theory is very simple for, it's very well known for this equation. It's not as difficult as the existence theory for the weak inverse curvature flow. However, you can use in some to get a uniform convergence on compact set to the solution of the weak inverse curvature flow, right? Remember this relationship, okay? For the inverse curvature flow, h is equal to the length of the gradient. And also formally, at least formally, actually there are contributions by Luca Benatti and Marco Pozzetta in which they try to Alessandro, sorry. Okay, okay. I beg your pardon. Okay, so Luca, Alessandra, and Marco actually they managed to make this form argument rigorous actually to prove that you can actually approximate the Hawking mass, right? The Hawking mass up to some factor. Okay. So I mean the question is there a new hope, right? So for the lambda positive lambda case, right? So this approach based on P harmonic function is a new hope because remember here's the main difficulty is okay here in this let's say in this speculation, right? So negative speculation. Actually, the problem was created by the fact that actually we were assuming the existence of this inverse curvature flow, right? Okay, landing on the boundary. We probably does not exist because if it would exist, okay, you get contradiction, right? And however, in this case, I mean, the existence theory is simpler, right? So if you instead of considering inverse curvature flow, you consider P harmonic green function or green function, okay, with zero Dirichlet boundary data, okay, maybe you can avoid this problem. Right. So is there a new hope? Okay, and here the green function strikes again. It's a very nerdy line. Okay, sorry, but okay, but in any case, over here the setting. So you have a compact tree manifold. Okay, with here, I mean the usual setting. You consider level set of the green function. After the P green function, already wrote the things with the P green function. So right, so you have this, and for any P between 1 and 3, actually everything works fine. I mean, concerning the existence theory. So the problem is, can we provide, can one provide actually the monotonic quantity, okay, that replace the Hawking mass, as I showed you in the lambda equal to 0 case? Okay, that's actually the case, right? Okay, the quantity is this one. Maybe I write it here. Okay. So at first glance, it looks weird, but actually I try to convince you that actually it is related. Actually, here is a version that holds for any lambda. Okay, but you can also, with lambda equal to 0, we recover the old formula. Here you have 4 pi minus lambda, the area of sigma tau. And here you have a density, so yeah, this factor, lambda p of tau d tau minus integral grad wp would be h minus, here you have another function, mu p of t, grad w, and that's it. And here you have the sigma, and you multiply everything by e to the lambda p of t, right? So this function, mu p and lambda p, okay, they satisfy structural relationship. Okay, so it looks weird at first glance, but actually it's a semi-decoupled system of ODE, right? Because the first one, okay, does not depend on lambda, right? So you solve first for mu, and then you substitute and you solve for lambda. What is AP? Well, alpha p, right? Alpha p is a geometric terms, okay? Alpha p that appears there actually is just given by this ratio, okay, in which h bar and wp bar are the mean curvature of the level set and the length of the gradient of the p-harmonic green function on the model space, right? So this is something that you can compute. I mean, it's not. I mean, in certain. So when lambda equal to 0 is just a number. It's explicit. That's the ratio between, okay, between the mean curvature of a sphere and the length of the gradient of the p-harmonic function on that sphere multiplied by 2, right? So in lambda equal to 0, that was very simple, very explicit. In lambda equal to 3, in general, is more integrated formula. I can write it, but it doesn't matter. Okay, here just mention that for the first computation that that we did for p equal to 2, I mean, some simplification was given by the fact that for p equal to 2, it is, again, something explicit, right? And so, but in general, if you impose this relationship, you have monotonicity, right? And here you see that the alpha p is precisely the one that makes this last square term be equal to 0 in the model situation, right? So this is kind of sharp. Right, and here the important. So here, I mean, so far I just imposed this ODE, right? And I formally compute the derivative, actually. But actually, if you want to say something useful, you have to select a special solution, okay? And a special solution, actually, you can prove a theorem in which you establish the existence and uniqueness of a solution with with these special asymptotics at t goes to minus infinity. So when you approach the pole, okay, you have to select a very special solution, right? Actually, it turns out that you can do that. There is just one solution that behaves like this, okay? It's not an initial data, it's okay, but it's like an initial data at minus infinity, right? And here, just I want to mention that everything simplifies in the lambda equal to 0 case, so the formula holds true for any lambda, but when lambda equal to 0 is particularly simpler because alpha p is a number instead of being a function, an intricate function. Also, mu p turn out to be the same number. E to the lambda p turns out to be this factor here, okay? And in particular, we'll see that if we let p goes to 1, you formally tends to the Hawking mass. If you take p equal, if you let p goes to 1, so if you take, for example, lambda equal to 0 and p goes to 1, you converge formally to the Hawking mass. Actually, it happens that the same happens also for any lambda, not just for p equal to 1. So in view of this canonical choice that you can perform, actually you can prove an interesting property of this quantity. So for example, a small sphere limit. So meaning that if you divide your quasi-local mass or whatever, so if you divide your quantity by the volume enclosed by sigma t, okay, and you let t goes to 0, so you approach the pole, right? What you get is the mass density at the pole, right? So that's yeah, it's a property that is reasonable to expect for quasi-local mass, right? So if you look to very tiny domains, actually you divide by the volume, otherwise everything goes to 0. Okay, what you get is the mass density, right? The mass over the volume, okay, has to go to the mass density. That's the case. You have the formal convergence that I was mentioning. So when p goes to 1, okay, you have the mu p goes to 1/2, e to the lambda p goes to this term here, okay? That's very evident in lambda equal to 0, right? Because lambda equal to 0, you clearly see that p goes to 1 implies that mu goes to 1/2, e to the lambda p goes e to the t over 2 over 8 pi, okay? In general, it's more difficult when it's much more difficult for lambda different from 0, but however, it is the case. So this means that if you fix t, okay, you have this formal convergence to the Hawking mass. I say formal because, okay, we didn't prove anything like this. So if you assume that the gradient goes to h, then formally your expression converges to the one of the Hawking mass. Okay, which a little bit scary, right? Because remember that the Hawking mass doesn't work in this case, right? Because if you have so because of the strategy that actually is killed by the counterexample. However, okay, at the end you see what was going on actually, and not only this. So you have a small sphere limit, which is fine if you want to define a quasi-local mass. The formal convergent to Hawking mass that is somehow gives you the idea that you are looking to something plausible in some sense, and also this let's say initial condition. These are not really initial conditions. So the initial condition that you give at the pole, okay, when t goes to plus infinity, actually they determines the solution up to plus infinity when you reach the boundary. Okay, actually you can study with some effort the asymptotic behavior of mu p and e to the lambda p when t goes to plus infinity, and you can actually write the limit of this quantity as t goes to plus infinity. So when you are really grabbing all the mass content, so this will be the expression of this total p mass of the thing, right? And so yeah, right. So when t goes to plus infinity, you have so that mp of tx as t goes to plus infinity, okay, approaches this quantity here. The boundary was assumed to be minimal, so the last term is not there. You have a sort of bulk term here, minus infinity plus infinity. Here you have 4 pi minus lambda area of sigma tau, okay? And here you have this e to the lambda p of tau d tau, and plus ap integral grad up over the boundary square. Sorry. Right. So right. So what do we get? So if we collect all this thing, actually, we have that for p between 1 and 3. Okay, we have the green function. You have the existence of this, and we can define mp of x. X was the pole. Okay, as this limit, right? And actually, you can also now you can let the pole was chosen arbitrarily at the beginning, but actually you can define, yeah, the p mass, the p total mass, let's say, as the infimum. Okay, you choose the pole that actually, that actually, yeah, the pole in which you realize the infimum. Actually, it turns out that uh, this infimum is achieved. Okay, there is a pole, okay, that realizes this infimum, so it's a minimum. And this is not. I mean, it's a technical lemma, but is essentially i- it's natural because what happens. So if the pole approaches the boundary, okay, these terms explodes, right? So okay, we want to exclude that it's not convenient if you want. It's not convenient going toward the boundary, right? And sorry, that is a minus, but actually it was a plus. Okay, sorry, this is a plus because it was written correctly on the blackboard. So here's the theorem. Okay, uh, the theorem is the following. So we have the usual setting. You have also to assume this assumption. So the relative homology for the second relative homology must vanish. This is an assumption that implies that the level set remains connected. Okay, the level set. Otherwise you have problem in the monotonicity formula. And so for initial data like this, you can prove that the infimum of mp of x, which you call mp, is non-negative. Moreover, since you know that this is achieved actually at some point, you can prove rigidity, right? So that was the statement that we were looking for since the beginning, right? So mass equal to 0, okay? So you conclude rigidity, right? So that's right. So you provide a reasonable replacement for the Minu conjecture somehow, right? And I mean the rigidity is clear if you so as soon as you know that the infimum is realized for some particular choice of the pole, then the rigidity can be easily deduced because you look to the monotonicity formula, you have a lot of terms that should vanish. So all the level set must be totally umbilic, the scalar curvature must be equal to C. So a lot of the usual path. Right, so, and to conclude, actually, here is what we learn from this approach. Actually, that the double limit does not commute in general. So what do I mean for the double limit? So you have, so if you pick the limit as p goes to 1 of mp mptx, actually what you get is, so this quantity formally converge to that quantity, okay, for any fixed d. If you fix t, okay, you converge to the Hawking mass of sigma t, right? So if you fix t, okay, let p goes to 1, you converge to the Hawking mass, okay? But then when you take, when you let t goes to plus infinity, okay, you have to let the Hawking mass go to plus infinity. And for example, if you are looking to the, if your setting is the one of the famous counterexample, this number, for example, you know that it goes to 0, right? Whereas you can do the opposite. So you, as we did actually, you first let t goes to plus infinity, so you get the total p mass, and then eventually, okay, you can let p goes to 1, okay? In this case, actually, the situation is simplified because actually you can prove that this extra term that I reported with the wrong sign once again actually is 0. Actually, it doesn't matter because when p goes to 1, this goes to 0. So actually, it would be tempting to define this limit as a m1, okay? And then, okay, and then we don't know, actually, it would be very nice. So for sure, this is a non-negative number, okay? But actually, the question mark is related to the rigidity problem. So if m1 is 0, can we conclude that we are on a spherical cap? That would be very nice, right? And I think that's all I wanted to say. Thank you for your attention.
Thank you very much for an interesting lecture. Are there questions?
Yes, I wanted to ask about these flows, the level set flow when p is not equal to 1. So is there a geometric way to write this flow? So does it depend on curvature normals? I mean, is there a more geometric way to
I
understand
mean,
this?
no, I mean, I guess the more dramatic interpretation is that it represents an approximation of the inverse curvature flow, as in Moses' paper, right? So the dramatic content is that. And then, I mean, of course, when you look at to geometric flow, these are, geometrically very, very interesting. Also, the monotonicity formula that you get are very expressive. In this case, I mean, at first glance, the monotonicity formulas are not as clean as the one that you get for the inverse curvature flow, for example. However, I mean, you gain. I mean, the advantage is on the existence theory, right? So
Yes.
because it's much simpler, right? Actually, you can. I mean, there are paper by. I mean, there is a famous paper by Moser, but there are also recent contribution by Mari Rigori Setti, in which people are using the. I also forgot to mention Koch Varnier also, in which people are using p harmonic function to prove existence of in the limit of an inverse curvature flow instead of the variational formulation. Okay, so that's the geometric intuition.
Thanks for the very nice talk. So you worded this whole approach as if the sign of lambda didn't matter, right?
Right. Well, I mean, the formal computation doesn't matter. The formal, and then I mean, of course, I could, I must be sincere. I mean, the lambda negative case, we didn't check you land on some well-known notion of mass, right? So for lambda equal to 0, of course, okay, because it was the starting situation that we analyzed with Francesca, Carlo, and Virginia. But yeah, it could be plausible that also with lambda negative, maybe it gives something interesting. I don't know.
Because then it would be the same thing that Francesca and Klaus Krönke and Pinois look at, right?
Could be actually. It could be. Yeah, in fact, that there is also this recent. Yeah, it could be right. So maybe you, at the end you pick this.
I mean,
this
they only
option.
do the p=2 case, right? But
They only did the pick. Yeah, sorry.
Yeah.
Yeah.
But-
Yeah, no, but actually it could be reasonable, right? Yeah, I didn't check but yeah, because our focus was mainly on lambda,
Of course.
positive lambda, right? Yeah.
And the fact that you did it with p bigger than 1 also would allow you possibly to do a Penrose, right? If you ask, instead of
Yeah,
starting
that
out
would
the
be-
point.
Yeah, that would be very nice. So actually, of course, a further direction would be to see whether you can use this method to prove a Penrose, but that's very hard. That's very hard. Yeah.
Thank you.
Thank you. So, as you pointed out, smooth solution of the inverse mean curvature flow cannot exist.
Yeah,
Because
only special
otherwise something
situation.
would go wrong.
Yeah, all the other special situation, right?
But what do you expect that it works? That there is a notional weak solution and something happens in the jump and that's where the gap is coming from?
I mean, I think that you may have. So the problem, I guess, is so yeah. No, thank you for the question. It's really, it was really one point on which we were struggling actually. So I mean, the problem is that if you have, I mean, the jump that you may experience here, they are fine because essentially you can treat by the same theory of Gerard and Tom. But if the problem is when you approach the boundary here. So because the behavior becomes crazy, the behavior of the inverse curvature flow becomes very crazy when you are approaching the boundary because you have a minimal boundary, so the speed for the inverse curvature flow becomes very large, and you lose control. I mean, that, yeah. So also in very special situations, so we try to perturb also to see what happens. So at the beginning, we wanted to just to take the limit of when p goes to 1. So try to reply the situation that is nowadays well known in the lambda equal to 0 case. Actually, you can see that actually the solution also when it reduces to an ODE, so everything is, for example, radially symmetric, you perturb just a little bit here. So you see that here the speed of the level set flow becomes crazy, and yeah, something goes wrong, right? You lose control in that region, so you smash
I
your
have my
flow.
own question there, but first the audience.
I might follow up on this. So the problem with inverse mean curvature flow in the sphere, for example, is that it doesn't know which equator it should go to.
Right.
Right. So if you start with an off-centered sphere, you will
Right.
completely lose control where
Right,
you go.
right.
So this symmetric picture is not maybe the right way to view, because you
No, no,
would
no.
you would have to design how this goes to this tip point very carefully.
Yeah, but also in that case, actually, also in when everything is rotation
Right,
symmetric,
of course.
also in that case you have problem because at the end you should have 0, right? So in that case you know that you land on something like this, but
But you have a non-symmetric background, so this symmetry.
no, but if you also if you cook up the background to be symmetric, actually, in this case, I mean, it's you really you know that you land here, but
But you have scalar curvature positive there, so it's not a space form.
no, it's not
So
a space
you
form. No,
don't
but a
know-
radial perturbation, a rotation symmetric perturbation of the space form gives some trouble.
Okay.
I have
Yeah.
this impression, right?
Okay.
So in general, you are right. Also in the space form, if your pole is here, this is very round, so it's a mess.
Maybe I get in one last question myself. When you go to the last slide, you had I have a question about the time parameter, because you said as t tends to infinity. Now for inverse mean curvature flow, the time is the logarithm of area. So in this case, when it goes to finite area, the time would only be finite in
Right.
mean curvature flow. So is
Right.
there a different time parameter?
Yeah, it's a different type parameter. Yeah. Yeah, it's a
Okay.
different type
I
parameter.
see. I see.
Yeah, because also, yeah, it's another, yeah, you're right. Yeah, in fact, right, you reach infinite time. With the inverse curvature flow on the sphere, starting from the pole, you reach the boundary in finite time, right? No, it's a different type parameter.
Right.
It depends on P, actually.
But it still might be interesting because you're choosing the optimal pole. So,
right.
you could also give inverse mean curvature flow the chance to choose the optimal starting point, right?
Right.
And
Right.
then it's not so clear whether maybe something still works. Yeah. So,
Yeah, yeah.
but
Yeah, my concern is about the fact that so if you prescribe that you if you want to land on the boundary, yeah, that maybe will cause to,
it's not clear that you can prescribe that. That's
yeah, right. That's,
exactly the point. Okay, I think we have to leave it here. And thank you very much for again. So it's a particular pleasure to introduce my colleague, Carla Zederbaum from Tübingen, and she will talk to us on combining potential theory with general relativity, a divergence theorem approach to proving geometric inequalities.
Thank you, and thanks to the organizers for the invitation. It's a great pleasure to be here, to hear all the talks, and in particular, it's a great pleasure to speak directly after Lorenzo, whose work inspired me to look more into this. So what I mean by combining it with general relativity, I don't only mean what Lorenzo just did, namely applying potential theory ideas in general relativity, but I want to show you somehow that the method that Lorenzo and Virginia devised has an origin in old work in general relativity, and there's sort of a continuous development that also can be used to simplify some of the arguments given in your work. So I'll start with this classical general relativity origin of these ideas, which is the black hole uniqueness. So here, physically speaking, the idea is that you have a black hole or a number of black holes, whatever this is, and I'll give definitions on a mathematical side in a second. We've heard a bit in Minguzzi's talk. And the physical intuition is that if these black holes, one or several, are in static equilibrium, so they don't move, and outside of them there is only vacuum, and they're isolated from any other influences, then there shouldn't be several ones because they should attract and start moving. So there should only be one. And because there's no reason to be otherwise, it should be spherically symmetric. And then from spherical symmetry, there is old work that implies that it will be the Schwarzschild system that you've seen in Gerhard Huysken's talk, and I'll write it again. So here is the setup for the mathematical formulation of this theorem. You have a three-dimensional Riemannian manifold with non-empty boundary. And you have this, everything is smooth in my talk, by the way. You have a smooth function f, which is positive on M, but 0 on the boundary. So f is 0 here. And this models what Ettore called a killing horizon, but really a time slice at a given time of a killing horizon. So that makes this into a horizon. And if you remember, Ettore spoke about degenerate and non-degenerate horizons in the static context that I'm talking about in vacuum. It's automatically non-degenerate, so we don't have to worry about these degeneracies that he discussed. And they solve a system of PDEs called the static vacuum equations, which reads like this. So the Hessian of the function is the function times Ricci, and the Laplacian of the function is 0, and this function is called the lapse, because it tells you in the space-time context, we can make a space-time metric out of this by a warp product. And then, oh, sorry, f squared. And then this tells you how time lapses in the space-time, okay? And then if you want, these equations come from the vacuum Einstein equations with 0 cosmological constant that Lorenzo showed you, and also Ettore showed you, once you plug in the special form of the metric. So this is where this equation comes from, and they're called the static vacuum equations. And now we have in our boundary conditions, we have PDEs, but we also have an asymptotic region, which we want to model an isolated system, so there are no external influences. So we have to put asymptotic conditions. And the asymptotic conditions we put is that outside some compact set, this is diffeomorphic to the exterior region of a ball. So M is the union of a compact set with the exterior of some closed ball. And this is diffeomorphic. And in the coordinates, how Anna explained to you when you define asymptotic flatness or asymptotic hyperbolicness, in the coordinates on here, I have coordinates xi, and these give me a radial coordinate, just like you usually do in Rn or in R3. In these coordinates, then, I'm asking that the Gij looks like the Euclidean metric plus imprecisely at the moment, more precisely later, lower order terms, and the function looks like 1 minus m over r plus lower order terms as r goes to infinity. And here m is a real parameter called the mass. And you should think of it as the mass of either your one or collection of black holes, the total mass of the system. Okay, so this is the setup. And then the claim of this black box theorem, which I'll tell you about who proved this, is that mg is isometric to the Schwarzschild manifold which has a mass parameter. So, and that mass parameter is the same mass as that shows up here, with F corresponding to Fm, where this is the lapse of the Schwarzschild system. And here, the Schwarzschild system is the manifold R3 outside the ball of radius 2m to absolute value of m. Let's do it like this for now. And the metric, the Schwarzschild system is 1 over Fm squared dr squared plus r squared omega, where r is the radial coordinate on this R3, and omega is my notation for the metric on the unit sphere. And this lapse function Fm is really only a function of radius and turns out to be the square root of 1 minus 2m over r. So if you expand this near infinity, you will recover these asymptotic conditions. As I said, this has a very long history. The first result in this direction was by Israel in 1967. And he put an additional assumption, namely that the differential is nowhere vanishing. And this already maybe suggests that he used a level set flow, but he didn't know how to handle the singularities. Okay, in particular, this implies that the boundary of M needs to be connected, so he only proved it for one black hole. And for his interpretation of the lower order terms, they have very strong asymptotic assumptions, but you don't really need all of these assumptions to close his argument. It's just traditional to ask for a lot of asymptotic rigidity there. Then next, there was a paper by Müller zum Hagen, Robinson, and Seifert in 1973, where they gave up on the condition that the gradient of f vanishes, but they still assume that the boundary is connected. And they sort of find analytic tricks to overcome the critical points. And the divergence theorem is already somehow involved. And then just a few years later, Robinson in 1977, again assuming connectedness, gave a level set flow approach using what was later called a magical divergence identity, and I'll explain that later. And so this is sort of this also a little bit, but sort of this is the history where we start getting into the world of potential theory. And then a completely different approach came up later by Banting and Masoudul Alam in 87. They allowed the boundary to be possibly disconnected. And they used the positive mass theorem that we've heard about in several talks already, the flat, asymptotically flat version of the positive mass theorem, and really only the rigidity. So they use very strong tools to get this disconnected, possibly disconnected boundaries under control. Now then, for a long time, at least in the three-dimensional case, nothing happened. And then Agostiniani and Mazzieri came in 17, again under a connectedness assumption. And they use a method very similar to what Lorenzo showed us today, but with an extra twist of a conformal transformation, which I'll mention more about later. So let me put potential theory plus conformal transformation. Then, where do I go? Here. Then just a year later, a maybe less well-known paper by Nozawa, Shiromitsu, Izumi, and Yamada, just 1 year later, again under a connectedness assumption, they prove the same thing with a magical divergence identity a la Robinson. However, I should warn you that there's a few problems with the proof. Let me write gaps here. And now there's a work with Alba Chiaracobo, who is going to come to Pisa as a postdoc in October, and Benedetto Leandro, who is in the audience, and Paulo dos Santos, which is on the archive since 2024, also under a connectedness assumption. We also find the magical divergence identity that allows us to prove this just out of the divergence theorem, and I'll explain more in a second. As a comment on the asymptotic assumptions, all these use very strong asymptotic assumptions. Of the form Gij looks actually like GMIJ, so the Schwarzschild system plus large capital O of 1 over R squared with two derivatives. So the first derivative like 1 over R cubed and the second like 1 over R4. And F is Fm plus the same type of error. Now Virginia and Lorenzo were able to, maybe I'll take red as well. Virginia and Lorenzo were able to reduce the asymptotic assumptions. So if I remember correctly, they ask for 1/2 minus epsilon, right? That's epsilon for some positive epsilon. And I think F is just Fm. That's, I think little o of 1 over R, if I remember correctly. And so here little o with an index has the same principle. It's the little o and the derivative as the little o of the derivative. And this asymptotic assumption here comes from the well-definedness of the ADM mass, as we discussed in Anna's talk, for example. Now, this paper again uses the old strong assumptions, but they don't need to, but they do it. And we use very weak ones. We have F equals Fm less O2 of 1 of R to the minus of R little minus 1. And Gij is delta Ij, and all we need is R to the tau for any tau bigger or equal to 0. So if you want, you can put O of little 1. But I do think that in principle, with the techniques you have now, you can do this here as well, Lorenzo, I think, yeah? Or with our asymptotic expansions. Okay, so the same problem also can be studied for n bigger than or equal to 3. And in fact, all the papers with a star treat that case. And the only thing you have to change up here is exchange all the R3s for Rns. And then here, you put a power n minus 2. And as well here, you put a power n minus 2. Okay. And then the same things hold. And there is 2 types of proofs. Again, the ones I mentioned. And then Banting-Masood-Lallam style proofs that adapt the positive mass theorem based argument to higher dimensions. And just for completeness sake, let me mention that the first such result was proven by Wang in 98. And then there is a paper by Gibbons, Ida, and Shiromitsu from 2002, which has a small gap that can be fixed though. And then I have work on this on the archive from 17, and then the more extended version that's more pretty, work in progress. And then there's a version by Rouleau in the spin case from 21, based on ideas by Walter Simon. And I should say that all the papers with a star need an additional assumption which replaces the use of the Gauss-Bonnet in the 3-dimensional case. And the assumption, maybe I erased something, I can't reach it. The additional, all the starred papers need the additional assumption that the integral over the boundary of the scalar curvature on the boundary integrated over the area element is less than or equal n minus 1 times n minus 2 Sn minus 1. That's the area with respect to the canonical metric. And now I'm multiplying this by the area radius, where this is computed with respect to the geometric metric on M to the power n minus 3 over n minus 2, n minus 1, sorry. So in the 3-dimensional case, this is given to you by Gauss-Bonnet. And in higher dimensions, this is an assumption related to the Einstein-Hilbert functional and very closely related to the Yamabe problem. Okay. So then for the rest of the talk, let me ignore these Banting-Masood-Lallam positive mass theorem style proofs, and let's go to the Robinson, Miller-Zim, Hagen, and our proof with Kogo, Leandro, and Paulo dos Santos. So the idea of the proof with this magical divergence identity is as follows. Recall you have a harmonic function, which was the lapse, like in Lorenz's talk and all the forthcoming potential theory talks. And then in addition, in this case, we have this other static equation, which is a lot more than you would know in other settings. And the idea that Robinson had, that I'm going to write to you in the n-dimensional case, introducing a parameter p, as Lorenzo showed you, is interesting to do, but I don't introduce it in the equation because the equation comes from physics. So I introduce it just in a vector field. So what Robinson did, he wrote an ansatz for a vector field of a specific form, some function of f. For convenience, let's write it like this. The gradient of f to the power p minus 3, gradient f squared, plus g of f, gradient f to the power p minus 1, gradient f. This is an ansatz. Robinson had this ansatz for p equals 3 and n equals 3. And if you study the Müller-Zum-Hagen-Robinson-Seifert paper that's older than the Robinson paper, and you read it several times, then you discover that this Müller-Zum-Hagen-Robinson-Seifert paper in some sense does something similar, but for a number I will call P3 that will become clear later, and n equals 3. So introducing this parameter P gives you somehow a bridge between these two papers. But we can write this in any dimension. And with this ansatz, or maybe let me explain the idea of the ansatz. You're thinking of a level set flow, so this is in the direction of the normal of the flow. And you're thinking of trying to prove spherical symmetry, because Schwarzschild is spherically symmetric. What happens in spherical symmetry is that the gradient of f absolute value is a function of the lapse itself, right? Because it's constant on the level sets. So then computing its gradient is another vector field that in the model case in spherical symmetry will be parallel to this, but otherwise will be not parallel. So you're saying, okay, what I want to have is a vector field that in spherical symmetry is the right multiple of partial r to be divergence free. But in general, not. But the hope is, and that's the magical divergence identity, that I find functions f and g so that the divergence of this is always non-negative. So there's a task. Find f and g such that the divergence of x is non-negative on M. And in the model, so in the Schwarzschild case, x is some constant times fm of r over r to the n minus 1 partial r. Let me call this constant a for some a and r. Why this specific form? Because you can compute in a metric like the Schwarzschild metric over there that the only radially symmetric divergence-free vector fields have this form. And so how you do this, you compute the divergence, you get derivatives of f and g and other terms, and you collect them in a smart way, that there are some that you like, I'll say more in a second, and some that you don't like. And the ones that you don't like, the coefficient will be in terms of f and g and their derivative, and you define those as ODEs, as we have seen ODEs come up in Lorenz's talk. You just make them go away by saying, I want f and g to solve those ODEs, and the remaining terms should be non-negative. So in this case here, what we find is that if we choose f of t equals, the formula is not important, it's just the structure of the formula that I want to show you. 1 minus t squared n minus 1, p minus 1 over n minus 2 minus 1, and g of t some other explicit function in terms of f and something else, so doesn't matter, where c and d are real numbers. And again, this comes from solving the ODEs that magically I defined, like in Lorenzo's case. Only in this case, you can explicitly solve the ODEs, and they're linear and coupled, and so you get two in first order, and you get two free constants, C and D. And then with these choices, you get the divergence of your ansatz vector field with these choices can be written as the gradient of f to the power p minus 5 times the function f of f into, now again, the details are not so important. The important thing is that we know that f is non-negative, and now I'm multiplying it by a square of a tensor t that I'll write in a second, plus p minus some threshold pn over 2f gradient f squared plus 4 n minus 1 over n minus 2 f gradient f squared over 1 minus f squared gradient f squared. So this is manifestly a square, this is manifestly a square, this is a threshold. So if I ask p to be bigger than or equal to the threshold, then this will be non-negative. Yes? So you have the harmonic equation, you are 1 at infinity, you're 0 on the boundary, so you stay between 0 and 1 by the maximum principle. You're 0 on the boundary, and because it's a black hole, and you're 1 at infinity. Thanks for the question. So if you can manage to have this bigger than 0 or equal to, and you have p bigger than this threshold pn, which turns out to be 2 minus 1 over n minus 1, then this will be non-negative. Now I owe you a definition of the t. The t is, let me get the signs correct, f times the cotton tensor minus the Weil tensor applied to gradient f. So it's a tensor very closely related to conformal geometry. Why is this natural? Because Schwarzschild turns out to be conformally flat by spherical symmetry. So something that in 3 dimensions, the Weil tensor vanishes. So then Robinson and Müller-Zimhagen, Robinson, and Seifert only had the cotton tensor, which is a conformal invariant in 3 dimensions. Now in 4 and higher dimensions, the Weil is the conformal invariant. So this guy is not conformally invariant. But in combination with the static equation, it turns out to be serve the same purpose. And similar tensors arose in the analysis of Ricci solitons by Cao and Chen, and also for quasi-Einstein metrics in a number of papers. Okay, so this is T. Now, let me explain this term. Something similar also arose today already in Lorenzo's talk. This is the relationship between the gradient f squared and the gradient f that I mentioned in the beginning that you will get in the spherically symmetric Schwarzschild case. So this is exactly what vanishes in the model. And so now all I need to do is I need to pick the parameters so that f is non-negative. And it turns out that this is equivalent to asking these two affine or convex inequalities. Okay? So now why did I want a magical identity like this? Well, because now my divergence is non-negative for all these parameters in this range, and all the p's bigger than or equal to pn. And so now if divergence x was integrable, I can apply the divergence theorem and get inequalities between the inner boundary and the outer boundary. And it turns out those are exactly what you need to close the argument. And I won't go into the details because it's long. Okay? So, but I'll write down schematically, you will get div x greater or equal to 0. And then using analysis similar to analysis used, say, by Virginia and Lorenzo in the Wilmore inequality case, or like this. You will be able to show by modification and measure theoretic arguments and some real analyticity of F that the divergence is in L1 under a condition on the power P. Where's the ansatz? Up there. So you see that depending on P, the singular set gives you more or less problems. And magically, and I can't explain this, the condition on P that you get is exactly the same one that you get from this non-negativity condition. And this is a thread in this kind of problems that we don't understand why very, very thoroughly. So then what you get is that G x nu at infinity dA is greater or equal to G x nu dA at the inner boundary for all the x's that come out of all the choices of these parameters. But because everything is affine in the parameters C and D, this turns out only to give you two inequalities, which together with this assumption on the scalar curvature that I guess I erased, that in 3 dimensions is the Gauss-Bonnet and in high dimensions some Yamabe thing, gives you the black hole uniqueness. So one equation plus the assumption plus the other equation saturate both equations. So all I need to understand is the rigidity, and the rigidity is boiling down, because this could be 0, so I can't use this latter part, is boiling down to analysis of when this T tensor vanishes. And this turns out locally to be quite complicated, but if you have asymptotics like we have, these are enough to show that you're Schwarzschild. Okay, let's say plus rigidity analysis. So just to recapitulate, we made an ansatz for a vector field inspired by the spherical symmetry of the model. We found functions by postulating ODEs that made the problem as simple as possible. Then we got a non-negative divergence for a 2-parameter family of vector fields, which by linearity is really only 2 vector fields. All the others are linear combinations. And we found a good threshold that worked both for the analysis, so the integrability of the divergence, and for non-negativity simultaneously. And then we were able to conclude just from the divergence theorem. So I mentioned this paper by Notsawa, Shiomito, Izumi, and Yamada, and they essentially tried the exact same thing, except that their handling of the critical points doesn't work. And also they forgot that if you have a term like P minus Pn, that you cannot use this in the borderline case. Do you have a question? No, okay. Okay, so. And before moving on, I should maybe say that in the paper with Alba Chiara Kogo and Benedetto Luando and João Paulo dos Santos, we also proved many more results on inner boundaries that have different properties. It's just that I'm explaining it in this case that's more well known to link it to the rest of the talk. Okay. Good. So now I mentioned to you that previously there was a potential theoretic proof of this by Agostiniani and Mattieri, and let me relate our approach to theirs to give you some idea. So in a nutshell, what they do is they write down a functional UP, and we manufactured our parameter to match it to theirs so that we can compare it more easily. And their functional is 2m. They assume m to be positive, or they show, in the black hole case, you can show that it's positive a priori to some power, n minus 1, p minus 1 over n minus 2. The integral over the level set, so this is where f is t, for this number t, gradient f t dA. So it's a similar functional that appears in classical potential theory now for this Leb's function. And they rescaled it such that it's constant on the Schwarzschild model, and they needed to include the M. And this is maybe the first difference. If you look at our vector field and the functions f and g, they don't depend on M. And if you want, by analogy, you can write a functional HPCD from our vector fields also by writing them as Gx, and now I'm putting CD here to explain the dependencies, what is suggested by the divergence theorem. And now you can compare these two functionals. They're both well-defined and continuous and have other properties that are not so interesting now. But what's interesting to observe is that you can express their functionals in terms of ours and vice versa, or their functions. Put it downstairs, okay. -1, 1 of t, minus HP10 of t. And also the derivative of their functional, which plays a big role in their proof, by mu p times t to 1 minus t squared h p minus 1 of t, where mu p is some constant computed from the mass and from p. And it's positive. Okay, so if you think about it, the fact that our vector field was in L1, on regular level sets, very clearly this is well defined. On singular level sets, you can give standard arguments to show that this can be extended continuously for all C and D. And that gives you, from this formula immediately, that their functional has a continuous derivative, and you can also get some convexity if you play this game further. And so in some sense, what I'm trying to say is that going to the physical space rather than to a conformal cylindrical model, as Agostiniani and Mazziri do, and doing the divergence theorem as an ansatz already directly in the physical space gives you functionals where you don't have to take derivatives of, because you already started with the divergence theorem, and gives you sort of convexity for free and things like this, like you later did in the positive mass theorem and Penrose also. One more comment. If you don't want to reproduce the three-dimensional Robinson and Müller-zum-Hagen-Robinson-Seifert, instead, in the process, you can, with the same ODEs, so with the same collection of terms, you can use the Kato identity for harmonic functions and instead produce other positive terms here related to the second fundamental form of the level sets and get the same argument as we've seen in many potential theory explanations. So somehow in this, under the static Hessian equation, this T tensor is closely related to the Kato identity. Okay. And now you can think of, okay, what happens if I take this method and go to other classical inequalities, like the Willmore inequality on Rn, the Minkowski inequality on Rn, and other inequalities that are more recent, like the Willmore type inequality by Agostiniani Fogagnolo, who is also here, and Mazziri for reaching non-negative manifolds and things like this. And it turns out the method surprisingly works in all these cases. I mean, all the ones we've tried. So let me give you examples. So the Willmore inequality on Rn for smooth domains with smooth for domains with smooth boundary works. And here the PD you look at is exactly the one you want to think about the electrostatic potential, So this is in outside your domain. You want U is 1 on the boundary in this case for historic reasons from electrostatics. And U goes to 0 at infinity. And then again, you write an ansatz. X is f of U, gradient of U. Now let's write it a little bit different because the computations are simpler, but the idea is exactly the same. Gradient U, beta gradient U. For some beta, which now takes the role of P plus 1. And you compute the divergence, you collect the terms. When you take the divergence of this term, you use the Bochner identity. Then you get the Hessian, you estimate the Hessian with the Kato inequality for harmonic functions again, and you get the divergence once you collect the terms that you don't like and make them ODEs. And again, you can solve the ODEs very explicitly with 2 parameters, C and D, that turn out to have exactly the same validity range. And then for beta equals, you get the threshold. In this case, it's n minus 2 over n minus 1, so it's just barely smaller than 1, which is both, again, the integrability threshold for the divergence and the threshold for non-negativity of the divergence. And we don't quite understand why this happens. I'm not sure if you see this in your proofs as well. And then you can close the argument for beta equals n minus 2. You get the Willmore inequality, combining the 2 inequalities you get from the 2 vector fields for the 2 extremal choices of C and D, in this case with a Hölder. You can also do, maybe I should put it here, this just appeared. And then you can do the Minkowski inequality on Rn, which was done by a master's student in our group, Florian Babisch, this year for convex omega, because then you don't have critical points. And here he uses the P-Laplace equation in M without omega. U equals 0 on partial omega, and you 1, and you're going to 0 at infinity. And if you use the P-Laplace equation, you want to have the same ansatz as before. But now remember what I told you about the ansatz. I want that this sort of is the normal to the level sets of U, and this should, in the model, which here is the Euclidean ball in both cases of Willmore and Minkowski, to be the gradient U would be the absolute value of the gradient of U would be constant on the level set, so this would also be radial. Now, if I use the P-Laplacian, I need to add a term which is already perpendicular to the level sets with a free function here, and I get 3 coupled ODEs. But they can be solved explicitly, and there will be 3 parameters, and the story will change a little bit, but other than that, nothing surprising happens, and you get the Minkowski inequality. And this is a result that was proved by potential theory by Bogagnolo, Materi, and I forget the third. Sorry. Pardon? Pinamonti, thank you, and Pinamonti. And this can be done also for non-convex omega, handling the singularities, and that's work in progress we're doing with Babisch and Ariadna Leon-Quiros, who's here as well and had a poster on this. Also, you can use exactly the same ansatz to get the Willmore inequality on Ricci non-negative manifolds with Euclidean volume growth, in effect with the same F in G, reproducing the Agostiniani-Fogagnoli-Mazzieri result. And it seems, but we haven't fully checked this, it seems that the exact same functional also reproduces the Ricci pinching result by Alessandra, and now I need to look, otherwise I will forget people's work. By Luca Benatti, who is here, by Carlo Mantegazzi, by Francesco Ronzio, and by Alessandra Plura, which has also been proved by inverse mean curvature flow by Husken and Kerber, and by Ricci flow by Lott, and Oriol Schulze Simon, and by Peter, who is here, and Lee. So we can reproduce the Ricci pinching, it seems, but there are some details to be checked. Also, just from this ansatz, combining these two results from potential theory in a very natural way. And also this seems to be possible to generalize to the Ricci non-negative case. And we don't know what happens under the pinching condition yet. So we can also generalize this method to include, for example, in the black hole case, include electric fields, which is interesting from maybe a physics perspective rather. And we are in the process of trying to see what happens if you try to do the positive mass theorem in the asymptotically Euclidean range that Virginia Agostiniani, Francesco Ronzio, and Lorenzo Mazzieri did. And what we find is a slightly more general family of monotone functionals than the ones you found. So there are additional terms that you can add that also give it. So it seems that making the ansatz in the vector field and not the functional sort of gives you some more freedom in what you can do. So I guess I would like to end by saying that somehow the more I saw of these potential theory papers, also in various other applications, the more it made myself think that this is all the same as the Robinson somehow. And we're very glad that somehow this sort of more direct method of working with the vector field ansatz directly in the physical space and not having to go to a conformally equivalent manifold as in the previous potential theory papers gives you two functionals instead of one functional and its derivative. So somehow the analysis becomes much simpler, as well as the geometry, because you don't have to do the conformal change. And in particular, the rigidity arguments always get much simpler somehow. Thank you.
I can speak. It's here. Thank you very much. Are there questions?
Thanks for this lovely talk. How far do you think you can push the Minkowski inequality? In terms of the domain, what do you assume?
In terms of regularity?
In terms of geometric properties, I mean, there are more general versions as a convex case for it. Like you have a star-shaped mean convex.
Okay,
you can,
so
it's open for mean convex and stuff like this.
So in the Euclidean space, Lorenzo Mazzieri and Mattia Fogagnolo and Pinamonti and maybe Virginia, and Virginia Agostiniani pushed it to general omega with smooth boundary already. And we can do exactly that too.
Can you write down your Minkowski inequality, please? I don't believe that.
Well, there's
outward minimizing.
You have to use the outward minimizing hull in the left-hand side.
Do you expect to remove that with this method or no?
No.
Okay.
You get the outward minimizing hull there.
Okay.
Yeah.
Okay, thank you.
Yeah, sorry. Should have said that.
Any other?
Yeah.
Any other comments, questions?
Thank you very much for the interesting talk. So I was wondering whether also in the first situation, the one of black hole uniqueness theorem, so I was wondering whether this more general identity maybe could handle also the case of several black holes. I don't know. That would be very nice, right? Because so far, I mean, this case can be dealt only with the post-mass theorem, right? So,
Right.
whereas, because maybe
not with using the Gauss-Bonnet for the same reasons why you don't get it with the Gauss-Bonnet. So I guess with the appropriate assumption on the integral of the scalar curvature over the total boundary then, right? But that's a very unnatural, I mean, that follows immediately that if you assume that if you have the total integral over the boundary mean scalar curvature over the boundary, if you make that.
So if you start like banding it, you double the things and then try to build your.
We tried that both with your method and with ours. And the point is that in the doubling, you sort of have the one monotonicity on one side, and then on the double, you have the opposite monotonicity. Yeah. So by the double,
Speaking back in so you double, but then you close one end, right? So
to do that in the conformal picture.
One end, one end.
That could work, and then do it out of the points that you glue in, like you do it in the positive mass theorem. That could work because you naturally, from the Banting-Masood ansatz in all dimensions, you get a harmonic function in your conformal picture automatically, which sort of has well understood poles at the glued in points. So that could work for one end, not for multiple ends, because then you will have singularities, but for one end that could work. And in fact, if you study this T-tensor closely in combination with the static equation, then you can rewrite it somehow as the Ricci of the conformally transformed thing in the Banting-Masood. So that suggests that there is a very close connection. Yeah.
Any other question? I have a question for the handling of the critical points. Is it for all these examples that you mentioned, is it the same analytic technique to handle the critical points, or are there differences between the various?
You can use the strongest one to deal with all. Okay, and I should say that we learned that method from Virginia Agostiniani and Lorenzo Mazzieri's paper on the Wilmore inequality on Euclidean space, where I think it's the perfect technique to deal with all the harmonic cases where the function is real analytic. And then there's slight modifications where you need to use weak versions of the co-area formula when you want to handle the P-Laplacian. But the idea is the same, but it's also the same that's already from them. So I guess if you want, you can do simpler things in the simpler problems, but there's this sort of uniformized method that handles it in all cases, so you don't need to reduce complexity, the easier ones.
Okay. Well, then thank you very much. Thank Carla again. Our last speaker this morning is Luca Benetti, and he's talking on nonlinear potential theory through the looking glass and the Riemannian-Penrose inequality we found there.
So thank you very much for the kind introduction, and also I want to thank the organizer for inviting me here this beautiful conference. I really enjoyed the talk since now, and I think there will be more interesting talk in the next 2 days. So today I would like to present this topic, which is a project that has been ongoing for the past 3 years. And well, let me say that this adventure to the looking glass would not be possible without the contribution of my co-authors, Mattia Fogagnolo, Lorenzo Mazzieri, Alessandra Pluda, and Marco Pozzetta, who are here at the conference, so the travel was quite safe. And yeah, we learned something in this trip, and so I would like to tell what it is. And so I divided the talk into 4 parts. The first one is introduction, or rather is more about the physical intuition behind the theorem. And then I will state the main theorem, and I would like to give you the 2 ingredients in order to give the proof and how we overcame the main problem. So let's start on following the white rabbit down the black hole, and I give you this short introduction. I hope it's helpful for some of you. So the main conjecture I would like to prove, not in the general case at least, but well, the general case is the following. is the Penrose inequality that roughly says that if you have a time slice in a isolated gravitational system with some given energy condition, then the total mass of the gravitational system is at least as large as the one of a black hole with the same area of the apparent horizon. So I just wrote it here so you can follow it during the talk. And well, let me say why this inequality should be true. If you start from, well, a time slice, which is, well, some kind of manifold, then thanks to Choquet-Brouillard and Garrosh theorem, we can evolve it in time. Now, if you have an energy condition and you have some energy mass concentrated in a relatively small piece of space, then we know by incompleteness theorem, by Penrose, that the gravitational, the Lorentzian manifold is future-like, geodesically incomplete, and so a singularity may appear in the future. Now, Penrose was aware that this is a problem, of course, and so introduced hypothesis to avoid this problem, which is known as the weak cosmic censorship, that says morally that singularity may appear, but they are always shielded, or at least generically they are shielded by an event horizon. So the Penrose inequality is a way to geometrically test the validity of this cosmic censorship hypothesis. And the idea is the following. As soon as the event horizon is generated, then this area cannot decrease. This is known as the Hawking-Garriott theorem. And the mass cannot increase. So mass cannot be created, can only be radiated to infinity or can fall into the black hole. So what you may expect at the very end is that you end up with a unique black hole, maybe rotating, but for which the Penrose inequality holds. Okay, this is just heuristic, and if you go back in time, what you see using this two monotonicity, that the same inequality must hold from the very beginning. Well, this is not the proof, it's the heuristic situation what we are in, and of course, the statement I wrote here is quite rough, and there are no, let's say, mathematical meaning of the terms appearing in the statement. So let me go farther into the details. So let's start picking each term and say what each term means. So what is a time slice? For me, is an initial data set, which is a tripole. We've seen it many times during the talks this morning and also in the past days. A tripole, MG is a Riemannian manifold, and K is a symmetric 0-2 tensor, and as in the previous talk by Lorenzo, we have these two constraints, and one representing the energy density and the other one representing the momentum density. And now, what is the energy condition I have in mind is the dominant energy condition. So the energy density is at least as large as the norm of the momentum density. And for the rest of the talk, I will be mainly interested in the case, the time symmetric case, so when K is equal to 0. In this case, the dominant energy condition is easier. It's just scalar curvature greater or equal than 0. And also, the horizon is quite easy to describe because in this case is an outermost minimal surface, so it's minimal, and no other minimal surface is shielded from the infinity of the space. And well, last but not least, I would like to say what it means to be isolated. Being isolated means that at large distances, let's say the influence of the gravitational field is almost negligible. So the space where this happens is the flat space where everything is null. Then the assumption, mathematically speaking, the assumption of being isolated can be interpreted as being asymptotically flat. So I would like to specify what means being asymptotically flat with a given order and a given decay ratio. So CK tau asymptotically flat manifold are those manifolds that are diffeomorphic to R3 minus a ball, and the metric is converging to the flat metric with a given order and a given decay ratio. So K will be the greater derivative I can take in this definition. For example, if I say that my space is C11 asymptotically flat, it means that G converges to the metric delta as x to the power minus 1, and the derivative of G converges to 0 as x to the power minus 2. Okay, now I have to say what I mean by a black hole with some mass, with a given mass, and the idea is, as in the talk by Gerald Wisken, the spatial Schwarzschild manifold, and also in the talk by Karl Cederbaum, we have seen it, but this manifold is diffeomorphic to R3 minus a ball, and the metric is conformally flat with this given factor in front of it, which is depending on a parameter m. So this manifold satisfies all the assumption I said before. Is the dominant energy condition all because it's scalar flat. It has an apparent horizon, which because the boundary of this manifold is outermost and minimal, and well, it's isolated. This is a one-dimensional problem because, well, it depends only on the coefficient in front of the Euclidean metric. Also, in this case, it's quite easy to define the mass, which is the area up to a factor, the area of the boundary. So the parameter m represents the mass, and in this case, the Perron's inequality holds as an equality, as you may expect. So this is, in some sense, the rigidity case of the Perron's inequality. Okay, so I would like to have a general notion of mass because I would like to compare it with the mass of the black hole, and we have already seen the notion I have in mind is the idea of mass. Let me give a rough idea why you can how can you interpret that notion. So the first idea you can have to introduce a notion of mass is to integrate the energy density, but this is a problem for two main reasons. The first one is that the mass of the Schwarzschild will be equal to 0 because scalar curvature is equal to 0. And also we have no superposition principle because, well, scalar curvature is not linear in the metric entries. So the main idea when you have something which is close to what you need but is not linear is to linearize it. And here we have something around which we can linearize it, which is the flat metric. For the flat metric, the first order, the zero order approximation is equal to 0 because scalar curvature is equal to 0. And the first order is just the gradient of the scalar curvature times the error, which in a given chart can be write in this form, which is a divergence form. I can integrate it by part and get the final notion, which is the ADM mass, the notion of ADM mass we've seen in previous talk. Okay, in giving this definition, I cheated a little bit because, well, this notion can be depends on the choice of coordinates, but actually this thing doesn't happen because, well, Bartni and Crucial proved that as soon as you assume something more on the asymptotically flatness, namely C1 tau with tau greater than 1/2, then the mass is a geometric invariant. Okay, so now I have all the terms appearing in the statement, at least in the time symmetric case. Before giving the ideas, let me give a look to literature. In the general cases, this is not a theorem. It's still a conjecture, even there are many contributions to it. In particular, recently it appeared on arXiv, this new paper where they prove a suboptimal Perron's inequality in the general case. Suboptimal means that the constant here is greater than 60 pi. What is really a theorem is the time symmetric case. As you may know, it was proven at the beginning of the millennium independently by Bray and Wisken-Ilmanen with two different techniques. The one by Bray uses monotonicity for conformal flow and, well, is based on the positive mass theorem. While the proof by Wisken-Ilmanen is based on inverse mean curvature flow. We have seen this flow many times during the previous talks. And, well, it's also another proof of the positive mass theorem, at least under these assumptions. Okay, during this talk, I will mainly consider the second proof, the one by Wisken-Mannen. And in particular, I'm interested in the relation with the one given recently by Agostiniani, Mantegazza, Mazzerio, Ronzio, which uses the nonlinear potential theory. We have seen it at work in the morning. And well, let me also say that there is another proof which is quite similar to this one by Xia-Yin Zhu. Zhu is here in the audience. Which is sharp version of spatial Schwarzschild and well actually prove Penrose inequality for the capacity of the boundary in a sharp way. Okay, this will be my setting for today's talk. So MG will be always an asymptotically flat Riemannian manifold with a negative scalar curvature, compact, outermost minimal connected boundary. Okay, so now we are ready to foreshadowing the fight against the Jabberwocky. So I can say the main theorem I would like to prove, and to do so, let me start with the previous one, the one by Wisken-Mannen. This is the statement of Wisken-Mannen proof. The setting is almost the same as I said before, except for two things. We have C11 asymptotically flatness and a lower bound on the Ricci curvature. And well, this is a beautiful theorem, and the proof is brilliant, while there is some, let's say, room of improvement because, well, we know that the ideal mass is defined even below the threshold given by the theorem. So even when the space is C1 so asymptotically flat with tau greater than 1/2, ideal mass is still well defined. So one may ask why we cannot prove it in this general situation. And well, of course, this will be the statement of my final proof, of course, but let me go step by step and see what the proof in the classical statement was. The idea is the following, and we have seen at work many times during this morning, the monotonicity formula for the Hawking mass. So Hawking mass, in some sense, compute the energy of a region surrounded by this sigma, the surface, by computing the deficit between the Wilmore inequality and the optimal one in the Euclidean case. These things is, roughly speaking, a constant. So if you compute the Taylor expansion of this quantity, the first order you can see is something that goes as 1/r. So you can multiply by something that goes as r, and you obtain something which is almost a constant. That's the rough idea. But it has interesting properties. For example, if you compute it at a minimal surface, we have seen it, the Hawking mass is the right-hand side of the Riemannian Penrose inequality. What we can do is the following. So we can evolve the boundary using the inverse mean curvature flow, which is this family of diffeomorphisms given by this law. So this flow is an expanding flow, and the speed of the flow is proportional to the inverse of the mean curvature. So if the surface is almost flat, the speed of the flow is faster, while in the points where the mean curvature is bigger. And so what you may expect at the end is something that is converging to something spherical, and actually what can roughly be proved, because, well, and with this and using the asymptotic behavior of the metric, what you can show is that the superior limit is bounded by the ideal mass. This is just converging properties. But the other interesting property is that the Hawking mass is monotone along the flow. So if you compute the derivative, we have seen this expression, you obtain something which depends on the scalar curvature of the surface, the trace second fundamental form, the scalar curvature of the ambient manifold, and this additional term, which is the tangential gradient of the mean curvature divided by the square of the mean curvature. Okay, this is non-negative, and if you assume that we are in 3 dimension and the surface does not disconnect, then the surfaces don't disconnect. You have Gauss-Bonnet theorem that allow you to say that also this part is non-negative. Okay, so in this way we can compare what happens at the beginning with something that happens at the end, and with this monotonicity we can say that this is less or equal than the NDM mass. But, well, this approach has a problem. Of course, we have seen it in the Lorenzo's talk. The problem is that, well, at the very beginning, you cannot even start the flow because you're starting from something which is minimal, and so the speed of the flow will be infinite at the very beginning. But even if you can start the flow, having to deal with diffeomorphisms means that you can't always say that the flow exists for all times. And this is for sure a problem for this approach. And the way to avoid this problem is, well, use level set flows. What you do is to replace your function with a level set of a function. Well, in this way, so the evolution will now be given by the boundary of the sublevel of the function, and what you can ask is to start from the starting surface by imposing that the starting surface is the zero level of this function. In this way, you gain something. You gain that the flow is defined for every time. So for every t, I have something to compute, but you have to pay something because you now have less control on the regularity. In particular, if you in this example, here you have something which is irregular, and also you have less control on the topology, which is a problem when you have to deal with Gauss-Bonnet theorem. Okay, in the rest of the talk, the topology problem will not be addressed because in our case, we know that the surfaces are still connected, so Gauss-Bonnet theorem holds, but in general, you can have as in this picture here. Okay, now we have some freedom of choosing this function. So let's see what happened in literature. We have two different approaches. The one by inverse mean curvature flow in the Wisken-Hillman paper, and the one using nonlinear potential theory. It's almost the same of the one given by Agostinelli, Mantegazza, Mazzieri, Ronzio, but well, here I prefer to use the other formulation, so the P Laplacian equal to the gradient of the function of Rp, for the reason that you may expect that this solution here should converge to the inverse mean curvature flow. So why is that flow related to the inverse mean curvature flow? Well, the idea is that the one Laplacian of the function, let me write it in specific, the P Laplacian of the function f is the divergence of the gradient of f to the power p minus 2, gradient of f. And well, if you take p equal to 1, this is the divergence of the unit normal vector field, which is normal to the level set. And so this is the mean curvature of the level in some sense. So this equation is saying that the speed of the flow, which is represented by, well, the inverse of the gradient, the norm of the gradient, is proportional to the mean curvature. While in this other case, this other theory is related to nonlinear potential theory for the reason we have seen in Lorenzo's talk, because, well, if you take the exponential of this function here, this function is p-harmonic. And what are the reasons to use this approach or this approach? Well, this is more geometric, as you can imagine. You have the explicit dependence on the mean curvature, while in the other approach we have more regularity, and also existent theorem is rather easier. So, well, if you have to do computation, maybe this one is better, but if you want to see something geometrical, this is for sure better. So let me show you let me show you what are the properties that, well, differentiate one approach to the other from the other. Well, first of all, regularity. Regularity for the inverse mean curvature flow is pretty low. They are only, in general, they are only Lipschitz. You could have fattening, you could have almost every problem, but instead for nonlinear potential theory, things are way more easy because the solution are C1 beta, and they are smooth away the critical set. And also, you have some regularity for the gradient of the function. In general, what you can prove is that the gradient of the function is in a Sobolev space. So if you want to do the computations leading to the monotonicity formula, this is something you would like to have because, well, it's easier to compute the gradient of the function at least, the gradient of the norm of the gradient, let's say. Well, in the case of level set, the thing is somehow switched. Level set of inverse mean curvature flow are more regular because they minimize a problem. They minimize the perimeter among all sets containing the level set. So every time you have something which minimizes the perimeter, you have some regularity, which is for free for minimization problem. So level set in our case is in this case is C11. And also you have a weak notion, geometric notion of mean curvature and second fundamental form. For nonlinear potential theory, you cannot have this, at least at the beginning, because the only thing you know is that the critical part, so the piece of the level set where the gradient is vanishing, is negligible for almost every t. And well, you also have something more. You know that the level set is moved away from the critical set, which allows you to maybe do some computation, define some mean curvature in analytic sense, but not in a geometric sense. Oh, they also have something in common. There are two energies associated with them. The one for the inverse mean curvature flow is the area of the boundary, or let's say the boundary of an hull, which is the strictly auto-minimizing hull. This quantity is the infimum of the area of all set containing the set K. While for the nonlinear potential theory, we have the P capacity, which is the infimum of the P Dirichlet energy. That constant there, Cp, is well, a normalizing factor. It's a quantity depending on P and on the dimension, which is 3 in this case, so I don't care about the dimension. Both of them are growing exponentially in time. So if you evolve your starting set by inverse mean curvature flow, the perimeter is exponentially growing. If you evolve the level set by using nonlinear potential theorem, the level set, the P capacity of the level set is exponentially growing. So this is something they have in common. And okay, so far so good. And now it's time to, well, give a little recap of what they say. Okay, sorry, I forget it. For P equal 2, all of these things are way more easy because in the perfect world of harmonic function, everything is smooth. Level sets are smooth for almost every t. So all computation are easier. So the idea in this talk is that, well, for P equal 2, you have something which is wonderful because you can do all computation you have in mind, but you don't have geometry. For P equal 1, you have a lot of geometry, but computation are more difficult. So in some sense, my looking glass is represented by the approximation you have passing from P equal 2 to P equal 1. And nonlinear potential theory is this mirror, let's say. So let me give you a quick recap of what I say so far. We have a technique based on inverse mean curvature flow that almost work if you have monotonicity of the Hawking mass and the convergence of evolved surface to coordinate spheres. The main problem now is that, well, having to deal with diffeomorphisms could be a problem, So because the inverse mean curvature flow does not always exist, and it could develop singularities. And a solution for it will be to pass to a level set or weak formulation. But of course, nothing tells you that the two ingredients to give the proof of the Riemannian Peretz inequality still hold if you pass to the weak formulation, because we have less regularity. So the rest of the talk is about, well, dealing with these two problems. So can we prove monotonicity despite the regularity of WP? And the other question is if level sets converge to coordinate spheres for large T. Okay, so let's start with the first question and find the allies to the T party. And I thank you, Lorenzo, because he said a lot of things I needed in this talk, so I don't have to repeat them. But I also blame on him because, well, he spoiled almost everything I would like to say in the next two slides. Okay, so the quantity you have already seen it, maybe in a different fashion, but it's the same. Is the what we call the P-Hawking mass, because, well, it will be clear in a minute why we give this name. It's almost like the Hawking mass. Here you have, okay, here you have replaced the area term with something which is tailored on P harmonic function, and you added an additional term there, which is related with the gradient of the function WP. And the reason why we call it P-Hawking mass is that if you take P equal to 1, as I said to you before, in this case, the gradient of the function is equal to the mean curvature, so this term vanishes. And the P capacity is the one capacity, which is up to a scaling factor, the area of the level set. So for P equal 1, this is the Hawking mass. But in general, this term here is non-negative, so this quantity has an additional property that if you remove the energy term from the beginning, you get something which is bigger than the Hawking mass. So in some sense, this family is approximating the Hawking mass from above. And this is not, well, only a formal idea, it can, sorry, a moral idea, but something can be proved at least at the beginning. If you take the starting level set, this additional term is greater or equal than 0, the mean curvature is equal to 0, so you end up with just the P capacity of the boundary. And we know by this work of Mattia and Lorenzo that the P capacity is converged to the 1 capacity as P tends to 1. So what you obtain is that the P-Hawking mass of the starting level set in the limit as P tends to 1 approximate from above the right-hand side of the Riemannian Peretz inequality. Okay, so as I said before, Lorenzo said almost everything, but let's see why this quantity is useful. Also for P greater than 1, we have a monotonicity formula. This is a recent work with Alessandra and Marco, where we proved that, well, for every P in between 1 and 2, you have this monotonicity formula for which, well, the derivative is bounded from below by this quantity. This is almost like the one in the Hawking mass. Here we have an additional term, which is this one. This one is a little bit strange, but if you take P equal to 1, you obtain the same term in the Garrosh monotonicity formula, because this is the mean curvature, the gradient of the mean. So sorry, the tangential gradient of the mean curvature. And, well, the interesting part of this theorem is that in one single theorem we have all the monotonicity formula explained before, and, well, let me say that at least for P greater than 1, this was proved by Agostiniani, Mantegazza, Matteo Ronzio, but just the monotonicity part. The expression of the lower bound of the derivative is not given in that paper. And well, let me also say that in this paper, so the mean curvature and the second fundamental form have an analytic meaning, not a geometric interpretation. Here we have a geometric interpretation in the sense of curvature variable, for those of you who are aware of it. And also, let me also say that in this case, monotonicity doesn't follow from an epsilon regularization limit, but just from computations, direct computation on the mean curvature, and the fact that we also prove a Gauss-Bonnet type theorem for level set of p-harmonic function, which is quite strange because in general, as I said, level set of p-harmonic function are not even C1 in general. And so they cannot be, in general, approximated by smooth level set. And even if you can do that, maybe you can not hope for approximation of the mean curvature and a second fundamental form in L2 sense. So it's quite tricky, but we managed to do that. And so monotonicity in this case follows from computation and the Gauss-Bonnet theorem applied here. Let me also say that, of course, the Wall theorem was already proved in Wisken-Ilmanen paper in the case p equal 1, both with monotonicity and the expression of the derivative. But there is a small difference because in their approach, they use epsilon regularization and they pass to a manifold with one dimension higher. Here we instead prove monotonicity by approximating the Hawking mass with a family of monotone function. So the idea is that we were able to prove that the family of p Hawking masses is convergent to the Hawking mass in L1 lock, and the expression of the derivative is lower semi-continuous as p tends to 1. So at the end, what you get is that the derivative of the Hawking mass is bounded from below by the quantity you expect from Wisken-Ilmanen theorem. And well, in this approach, of course, the difficult part is not in the computations, but well, in the proof of this convergence. Let me briefly explain why. The reason is that you would like to pass to the limit this quantity here, this inequality. And already in the expression of p Hawking mass, you already have the mean curvature, which for p-harmonic function depends on second derivative of the function WP. And the result that was known at the beginning is just a local uniform approximation of well, p-harmonic function to the inverse mean curvature flow. This was proved in Marie Golisetti paper after the work of Moser and Koshvar and Ni. So you only know that WP is converging to W1 locally uniformly, but you would like to pass to the limit something that depends on higher order derivative of the function. And what is really strange, what was really strange at the beginning is that what we really need is actually the monotonicity formula. And the reason is the following. It's hidden in this additional term here. Because if you imagine that this quantity is bounded, and you can prove it is bounded maybe in L1, this means that the integral of this function is bounded as well. But, well, in order to have this term here bounded, since you have this p minus 1 at the denominator, you need that this quantity goes to 0. So in some sense, this is telling you that the gradient of the function is approximated the mean curvature of the level set in L2. And so if you really use this thing, what you can prove, you can improve a result by Marie Golisetti by saying that you don't only have local uniform convergence, but you also have convergence in WQ lock for every q less than plus infinity. And let me say that this convergence is sharp, and you can imagine why, because, well, WP function are in C1 beta, and the limit is only Lipschitz. So you cannot hope for something better than q less than plus infinity. And also, using this property here, we also were able to prove that the level set are converging in a geometric sense, in a curvature variable sense. So we can make these other terms appearing here, so the second fundamental form and the mean curvature, which is not here but is in the the expression of the P-Hawking mass. Well, oh, sorry, it's here actually, but this you can cancel this other term, which is not appearing in the limit, but you get the convergence of the Hawking mass in L2 by exploiting this additional result here. Okay, so I have a lot of time. I can pass to the last part if there are no questions on this first part. Yeah. Yeah. Yeah, no, then okay. That's the reason why we have this greater or equal here. Because in principle, at the boundary, you may have a gap, you may have a jump, and well, this is not, well, we can only prove that, let me write in this way. Imagine that you have P-Hawking mass minus the P-Hawking mass of the initial data. This is greater or equal than the integral of, let's say, the derivative of the quantity. And what you can prove is that this is upper semi-continuous, sorry. So this passes to the limit, but what you get at the end is the inequality, not the equality. So in some sense, well, you cannot prove the theorem for the starting level, but just for almost every level in the interior. So in that case, you have a jump, and well, this gap. Okay, let me be more precise. In fact, for p greater than 1, we prove equality. Okay, but in the limit as p tends 1, we can only prove the inequality. And the reason is just at the starting level, because we may have the jump in the measure. So at the first time, we have the convergence if it's outer minimizing. I don't think so. I don't think so. Ah, no, okay, no. Okay, if it's minimal and outer minimizing, yes. But the problem is in the mean curvature. Because, well, this mass for P equal to, well, outer minimizing set and for minimal set is just P capacity. Well, this one is just the P capacity of sigma 0 with a given power. And this converges to the outer minimizing, the perimeter of the outer minimizing gala. In that case, you can prove convergence. Yes, you can prove convergence, but in general, you cannot. And the reason is in the additional term here that may jump at the beginning. So you just have a measure which is concentrated on the jump of the inverse mean curvature flow at the beginning. Oh, thank you for the questions. Okay, if there are no other questions, I can give you the last part of the talk. And this is, well, in this first part, I show you how we can use two different techniques. We have two different monotonicity formula. Now I would like to put them together to obtain the better result I claimed at the beginning. And so in this way, I would like to pass to the looking glass and see what happens from the perspective of the inverse mean curvature flow with respect to P equal 2. And well, let me say what is the main difference. Okay, I would like now to prove that the limit at infinity of the Hawking mass is less or equal than the ADM mass. In the work by Wisken and Mannen, they prove this beautiful, well, convergence that says, okay, W1 is converging to the model solution in the Euclidean space. And also you have some convergence of the level set to spheres for a large time. But in doing that, they have to assume something more. They have to assume something on the Ricci tensor. This was also true for the existence, but well, you can manage to avoid this problem if you use a recent work by Kai Shu. But well, what happens is that for the investment curvature flow, you have not enough asymptotic analysis in order to well pass to the limit in a smooth way, let's say. While for p equal 2, you are in the perfect world of harmonic function where well everything is possible because you have the representation formula. And with that representation formula, since everything is linear, you can prove better convergence result. So you can prove that the function W2 is converging to the model solution also with a given decay ratio, which is given by the asymptotic assumption on the metric. And this happens not only for the function itself, but also for the first derivative, and in an integral way also for the second derivatives. And in some sense, in the proof of this statement in Wisken-Hillman proof is because, well, you don't have enough convergence for the function, but you can avoid this problem by assuming something more on the convergence of the metric. So the error is compensated by the greater convergence of the metric. In this case, we in some sense remove the condition on the convergence by proving something more on the convergence of the function. That's the trade-off for these two approaches. Okay, so at the end, what we can prove in this case is that the 2 Hawking mass is less or equal than the ADM mass at the limit, with a small difference that here we are dealing with the geometric flow, while here we have the analytic flow, the harmonic flow. So in some sense, you would like to pass this condition here to the inverse mean curvature flow. If you do directly with the inverse mean curvature flow and harmonic function, the problem is that what you get at the very beginning is just a non-sharp upper bound, because here we use the things I said you from the very beginning, that in some sense Hawking mass is approximated from above by the p Hawking masses up to this energy term. Now, by monotonicity, if you restart the flow with the 2 flow from the set sigma t, sorry, this is again sigma 1 is the same we have here. If you start from the very beginning the flow, then you have this inequality here by monotonicity. But the problem is that you don't have a sharp upper bound on this quantity here. And the reason is that this convergence here is not enough to prove that this limit as t goes to plus infinity is controlled by 1. But, well, if you replace the 1 capacity and the inverse mean curvature flow with the p capacity, you can prove the point 1 and 2 even for p greater than 1 without this additional behavior. So you can only prove that logarithm of x, the WP is convergent to the model solution as the, well, with a error which with not the case. Let me state here. So what you can prove is that WP is converging to 3 minus p logarithm of x plus a constant plus something that goes as logarithm of 1 plus O small 1 of 1. So without the decay. So in principle, for p different from 2, it's not possible to do the same thing we did here. but at least you can prove that the behavior of the energy is exactly the same as in the case of for p equal 2. So if in some way we are able to replace the Hawking mass with the p Hawking mass, we could finish. But the main problem in doing that is the following, that if you recall the definition of the p Hawking mass, we have this additional term here that involves the gradient of the function, and in general we are not able to compare the gradient of function Wp with the gradient of the function W2. So two different gradients are not comparable. We are just saying that for p equal 1 this inequality holds, but for p different than 1 we cannot prove that. So what we can do, okay, now take any p in between 1 and 2. For large t, you have that this is almost spherical, and if you compute the derivative of this additional term, you get these two quantities here that are appearing in the computation for monotonicity formula. Now, the first one is the integral of the scalar curvature. You can use Gauss-Bonnet theorem. This is 4 pi, so you can collect 4 pi, and you get this quantity here, which is, well, the term appearing in the Hawking mass. So now, if you use this thing, that's at least asymptotically, the derivative, because what you need to have in mind is that my next step is to use the L'Hopital rule, because, well, I can use it as an exponential term, divided it by something that goes to 0, and if you use the L'Hopital rule, you get the derivative of this term divided by the derivative of this one, and the derivative of this one is the Hawking mass, at least the quantity appearing in the parentheses of the Hawking mass. So at least asymptotically, what you can prove is that the p Hawking mass behaves up to this energy term as the Hawking mass, and now I can use what I learned before, that the Hawking mass is controlled by the 2 Hawking mass. But 2 Hawking mass is controlled by the ADM mass, and now I have the same ratio I said you before that is behaving is behaving asymptotically in the same way. So this in the limit as t tends to 1 converges to 1. And now we have that p Hawking mass, the limit of all p Hawking masses is controlled by the ADM mass. To finish it, p Hawking mass is controlled by the ADM mass from the very beginning by monotonicity, and now I can pass to the limit as p tends to 1. And as I said you before, you obtain the right-hand side of the Riemannian Penrose inequality, and now I didn't use extra assumption on the metric. So the final statement is the following. We proved with Mattia and Lorenzo. Let's say with a slightly different technique. This one is not in this paper, is in another paper, but, well, the statement is in this one. So for the sake of, well, presenting well, is better to show it in this way. But, well, what we prove is that even in the optimal threshold, in optimal decay assumption, the Penrose inequality still holds. I want just to mention a couple of more things, because I have time to do that. We also proved in the same paper a Penrose inequality holding for the isoperimetric mass. Let me say roughly what it is. Instead of considering in the Hawking mass, which is, well, the deficit of the Wilmore inequality multiplied by the area constant, let's say, in the isoperimetric mass, you take the deficit in the isoperimetric inequality, and in this case, since this goes as r to the power 3, this goes as, sorry, this is 3 over 2, this goes as to the r to the power 3. In order to have something which is almost constant, you need to divide by the area of the boundary, and you call it isoperimetric mass of the set omega, which is, well, inside your manifold. And then you take the limb sup as omega invade the space of the isoperimetric mass, and then you take the soup among all possible exhaustion of your space. And with a relatively simple technique using the L'Hopital rule and a contradiction argument, what you can prove is that also the isoperimetric mass satisfy the Penrose inequality, even if your space is C0 asymptotically flat. And moreover, if you combine this theorem with the theorem with the core of the paper by Jaregui and Lee, you can prove that the isoperimetric mass is equal to the ideal mass under this optimal decay assumption, which in some sense implies again the theorem by Barton and Crucial. And the reason is that, well, you can prove this equivalence in a given chart. And now the isoperimetric mass does not depend on the chart. It only depends on perimeter and volume of the set. So this holds for every chart, and so the ideal mass does not depend on the chart you choose. And okay, with this, I conclude and I thank you for your attention.
Maybe a naive question. For your mass theorem about the monotonicity formula of the P Hawking mass, can you back to that slide?
Yeah.
The monotonicity inequality, the derivative.
This one.
Yeah. So why P require P less than 2, not 3, for instance?
Okay. I think you can do it even above the threshold. We didn't do that because, well, we had in mind to pass the limit as p tends to 1, and so we didn't do that, but I think you can do even if p is greater than 2.
Okay, so you said that in your proof, this result also true for p between 1 and 3, for instance?
Yeah.
Okay.
Yeah, it follows from the very same reason, because here the proof is just compute the derivative at points where you don't have critical, away from the critical set. Then you can prove that the critical set is not that important. And the other things you need is that, well, you have this, yeah, you don't even need that. If you use the analytic expression, you can prove it for every p in between 1 from 1 to n in every dimension. So in this paper, we actually, I didn't mention that, but we actually prove monotonicity, a very large family of monotonicity formula that holds in, let's say, every dimension with every condition, with any condition on the Ricci tensor. And in that paper, we also, well, let me just go back a little bit. The idea is that for every p, you are now able to compute the derivative of the integral of the gradient of the function in a given range of exponents, and also the derivative of h times the gradient. So you can compute them explicitly. So the formula is still holds even in more general setting. And we didn't do that, but I think in the same spirit of previous work with Mattia Lorenzo for the Minkowski inequality, we proved it for every p between 1 and 2, and then the dimension of the space. So I think you can do even in that situation.
Okay, but in the high dimension, do you have like a positive P Hawking mass?
No, you don't have the monotonicity. Okay. That's the problem. Yeah, okay, you don't have the monotonicity, but you're still able to compute the derivative. Okay. This is independent on the monotonicity, just the derivative of the function.
Yeah.
Okay. So the derivative, you can compute the derivative. What you cannot say is that this is greater or equal than 0, of course.
Okay, thank you.
Thank you for your questions.
I have one question concerning the approximation as p tends to 1.
Yeah.
Can you say something about that the directional vector field coming from the gradient of WP in some sense converges to the directional vector field that you get from inverse mean curvature flow?
Yeah, we can prove it. And well, actually, this is in some sense the starting point because, well, okay, starting from this, it's quite difficult to prove any other type of convergence because this is just a convergence of norm of the vectors, while you would like to have something more. And these things, well, comes from the convergence of the P capacity to the area of the level set. So,
Yeah, but I don't mean the norm. I really mean the vector.
Yeah.
Okay.
The vector. Yeah. What I was saying is that this is not enough in general to prove any further convergence,
Okay.
and actually in the paper we use this in combination with the convergence of the vector fields.
And what happens in the jump regions of inverse mean curvature flow? Is it
Okay.
in our approach we have to go to higher one dimension extra, and then there's a vector field upstairs which you could project down into the jump region. Is that the vector field you get?
Let's say no. It's well. Let's say this because well, otherwise it's quite difficult to understand. The idea is the following: for almost, if you take sigma p, the evolved surface by p, you can compute the unit normal vector field at almost every point because almost every point is smooth, and this can be done. For p equal 1, what we approximate is not always the unit normal vector field, but it's the unit normal vector field, just outside the critical set of let's say this V1 characteristic of M minus the critical set.
Okay.
So in some sense, this is 0 everywhere where the function is the inverse mean curvature flow is equal to 0. So where you have this flattening property, this is we impose it to be equal to 0, and this approximate it.
Okay, I believe the approximation outside, but it would be interesting to study whether in the inside you can also get a limit inside the jumping set and whether it coincides with the projection of the vector field that you get from the foliation in inverse mean curvature flow upstairs, one dimension higher.
We didn't try it.
That would be, I think, in terms of understanding the approximation, I think it would be very interesting to understand.
Yeah, I think so. We didn't try it because well, we were happy.
You don't need it for the inequality.
Yeah, of course.
Sure.
Yeah.
Any other question? Then thank you and thank all the speakers of this morning.